Here we have a problem. We have to plan the synthesis of this compound, an alkene. We know that one strategy to make carbon-carbon bonds is Wittig, in that we can make alkenes from carbonyls compounds, so aldehydes and ketones. So the first step will be disconnecting these alkene into two fragments. And there's a couple of ways of doing that, and we're going to do the analysis and see what is the best way. So say that I start from, one way of doing it is, this is acetophenone, and the other fragment I will need to have, let's say that I have CH2, and that's BPH3, and I need to make that the elide. Now, another way is to think that here I have the elide, and I have my carbonyl compound is methanol. So notice here what I did was inserting the O right here, so acetophenone, and then I have this fragment is one carbon with two H's, so that is my elide. And here I inserted the oxygen on this side, so this is where the Wittigs are. So we need to analyze what's best. So let's work on that side. So very simple aldehyde, so methanol or formaldehyde. And now, how do I make the Wittig? Well, I need to make this. Let's do the resonance structure first. Remember that when you do the resonance structure of the elide, you will have the following three: pH 3, this one. That is your elide. And that will come from following alkyl halide. So here, what you do to prepare the elide here is to make it react with triphenylphosphine first, and in the second step, you treat it with n-butyl lithium. So first, we're going to do an SN2 over to this carbon. That's my alpha carbon. And notice that this alkyl halide is secondary. So the first step will be doing an SN2 over here. And then I use butyl lithium to remove one H and get my elide. And that's the resonance structure. So I need to make the elide from a secondary alkyl halide, and then I will put these two together and we'll make the alkene. Now let's look at the other pathway. If we disconnect that way and put the O on this side, and here my fragment would be the elide corresponding to, let's do the resonance structure. Here I will have CH2 negative, BPH3 plus, so that means I'm doing this, and this comes from following alkyl halide. So how do I make this from metal bromide? First, I need to treat it with triphenylphosphine, and that is an SN2 reaction. And this is a primary alkyl halide. And so that's my first step. In second, I need to remove an H here, so I will use n-butyl lithium to remove that H. So this is how I do it. Once I have my elide, that with my ketone here, I'll make my target molecule. I'm gonna erase this because this I wrote previously. So this is what I have. I am planning the synthesis of this. And again, I am doing retrosynthetic analysis, like disconnection approach. Disconnected one way, and this is the ketone, and that is the elide it come from. Or I can put the O on this end, so I have methanol, and that elide is this one. Now, thinking of the mechanism of reaction, what synthesis is more efficient? So making the ELI here requires a nucleophilic attack and SN2 over to a secondary carbocation. That we know is not very good. Secondary alkyl halides react slower than primary alkyl halides due to steric hindrance. On the other hand, I have here a primary alkyl halide, not even primary, it's a metal. So it is the most reactive of all the alkyl halide is a metal towards SN2 reactions. So that method would be giving me better yields doing the SN2 reaction over the metal bromide than doing the SN2 reaction over to a secondary carbocation. So that step right there, this is preferred because I can make have more yield at the nucleophilic substitution at the SN2 reaction. So too much steric hindrance here. In that way, then, is how we select, say, my preferred pathway, then would be this. So first, I'm going to make my ELI from methyl bromide, and I'm going to make it react. I'm going to treat that with triphenyl phosphine and followed by butyl lithium, and then I'm going to add acetylphenone, and that get the alkyne. So that is the final strategy.